Economists have these big ideas all the time. Like, if people earn more, they'll probably spend more. It makes sense, but how do they actually prove it? How do they go from just a hunch to a solid prediction? Well, they do it by finding the secret signals hidden in the chaos of real-world data. And in this explainer, we are cracking the code on Econometrics, the seriously powerful toolkit that separates economic fact from fiction.
So here's the game plan. We're going to go step by step. First, we'll figure out what our tools even are. Then, we'll grab a famous economic theory and actually build a model for it. We'll see how to fit that model to real data, make sure our work is solid, and, in the end, we'll use it to solve a classic economic mystery.
All right, first things first. What exactly is econometrics? The easiest way to think about it is like a bridge. It connects these abstract economic ideas you might read in a textbook to the messy, complicated, data-filled world we actually live in.
I mean, anyone can have a theory, right? Like, on rainy days, people buy more umbrellas. It sounds logical, sure. But how would you actually prove it? How do you know it's a real thing and not just something that sounds good? That's the exact question that Econometrics was designed to answer.
And here's the official definition. It's this cool blend of economics, math, and statistics. But the key takeaway is this. It's all about using data to give us actual numbers we can work with. We can estimate relationships, check if our theories hold water, and even try to predict what's coming next. And this is not just guesswork. Not at all. It's a really rigorous step-by-step process. You start with a theory, you build a mathematical model, you go out and gather data, you estimate your model, and then you test your findings. It's a structured roadmap that takes you from a question to a real data-driven answer. Okay, enough with the abstract stuff. Let's make this real. For the next few minutes, we're all going to be econometricians. And the mystery we're trying to solve is one of the most famous ideas in all of economics, the relationship between how much we earn and how much we spend.
This idea comes to us from the legend himself, John Maynard Keynes. And it's pretty intuitive, isn't it? If you get a raise, you'll probably spend a little more, but you're also likely to save some of that extra cash too. You won't spend every single new penny you make. Okay, that's our theory. Now, how do we test it?
Well, first, we build a simple little math model. In a perfect world, in a lab, this relationship would be what we call deterministic. For every single extra dollar of income, spending would go up by a precise, perfectly predictable amount. It'd be this beautiful, clean, straight line. But we all know life isn't that simple.
Yeah, in the real world, a million other things affect your spending, right? Maybe your car has an unexpected repair, or you're saving up for a vacation, or maybe you just don't feel like shopping that day. To account for all this real-world randomness, we add something called a stochastic or error term. This little guy represents everything else besides income that could possibly affect spending.
So now we have a theory and a much more realistic model. The next job is to grab some data and try to uncover the pattern that's hiding underneath, that hidden signal inside all the real-world noise. Now, this is where it gets really cool, because this is real data. On the bottom axis, you've got the total income of the US economy, the GDP. And on the side axis, you've got how much people spent. Every single dot is a different year. It is definitely not a perfect line, is it? It looks more like a cloud of points. But you can totally see a pattern there. As income goes up, spending tends to go up too. And this is where the main workhorse of econometrics comes into play. Linear regression. The goal sounds simple, but it is incredibly powerful. Find the one straight line that best fits the data, the line that just slices right through the middle of that cloud of points, getting as close as possible to every single dot. This line is our best guess at the true relationship hiding in there. But hold on a second. Before we can actually trust this best fit line, we have to do a little quality control. Just like in any good science experiment, we need to check some really important assumptions to make sure our results are credible and not just some statistical accident. So the first rule is super simple. We're assuming the relationship we're looking for is a straight line. I mean, the tool is called linear regression, so our whole model is built on the idea that for every extra dollar of income, the effect on spending stays consistent. Rule number 2 is all about consistency. So check out the graph on the left. The data points are spread out pretty evenly around that line. Our model is just as good at predicting things at low income as it is at high income. That's good. That's what we want. Now look at the one on the right. See how the data fans out? Our model gets less and less accurate as income goes up.
For our results to be reliable, we want our model's misses to be consistent and random, not getting bigger or smaller in some pattern.
And third, we need to check for something called autocorrelation. It's a fancy word, but it just means that the misses of our line, those errors, have to be random. One error shouldn't help you predict the next one. For instance, if our model predicts too low one year, it shouldn't have a tendency to be too low the next year too. The errors can't have their own secret pattern going on.
Okay, so let's say we've passed all the tests. Our model is solid. We're ready to draw a conclusion. But first, we have to face the single most important concept in all of statistics.
Correlation is not causation. I'm going to say it again because it is that important. Correlation is not causation. Just because two things move together doesn't mean one is causing the other. The classic example, ice cream sales and shark attacks. They are very strongly correlated. They both shoot up in the summer. But eating ice cream doesn't cause shark attacks. The real cause, the hidden factor, is the hot weather that makes people want to both swim and eat ice cream.
See, correlation just measures how tightly packed the data is around a straight line. Like you can see on the left, a perfect positive correlation means the dots form a perfect line going up. A perfect negative correlation means they form a perfect line going down. Simple as that.
And a correlation near zero just means there isn't much of a linear relationship. But careful, this is a classic trap. Look at the graph on the right. The correlation there is also zero, but there's clearly a perfect, predictable curved pattern. So the big lesson here is that our tools are amazing for finding linear patterns, but we always have to think about what else might be going on. Okay, with that critical warning about causation tucked away, we are finally ready to solve our mystery. We've built the model, we've checked the rules, and now it's time to see what the data actually tells us.
And here it is. After all that work, our regression analysis gives us this simple equation, this formula. This is our best fit line. This is the quantified answer to Keynes's theory, pulled from 45 years of real-world data. But what does it even mean? Let's zoom in on the most important number here, 0.7218. In economics, this has a special name, the marginal propensity to consume. And all it tells us is that, on average, for every single extra dollar of income the U.S. economy generated between 1960 and 2005, about 72 cents of it went towards consumption, or spending. Keynes was right. People do spend more when they earn more, but not the whole amount.
So, think about what we just did. We started with a pretty general idea from an economist, and we ended with a precise, data-driven number. We turned a theory into testable evidence. And that is the real power of econometrics. It's like a lens that helps us find the hidden relationships that shape our world. The only question left is, what hidden patterns will you go out and uncover?